Hi everyone, I will be presenting the spotlight for leveraging shape completion for 3D Siamese tracking. Tracking is the problem of, given the initial location of an object, identifying that same object across time. In the case of tracking objects and images, this means someone identifies an object in an image by drawing a rectangular bounding box, and you must find that same object in future images. We refer to this object as the target. For 3D object tracking, instead of images, we generally use LiDAR point clouds since they can better capture the depth of objects. The bounding boxes for objects are thus not just rectangular anymore, they become rectangular prisms which must tightly capture the target. For most applications, this is further simplified into drawing a bounding box that is aligned to the ground plane. Thus, the bounding boxes are defined by 7 parameters, 3D coordinates, 3D dimensions, and a single rotation angle along the vertical axis. 3D object tracking is a very important prerequisite for autonomous navigation. Having the knowledge of not only where objects are, but also how they are moving in time allows an autonomous agent to intelligently plan their motion in order to avoid collisions with other dynamic objects or agents in the scene. This is especially important for the task of autonomous driving, where an autonomous vehicle must avoid dangerous situations like getting too close or colliding with other vehicles on the road. A useful way to approach 3D tracking is by splitting it into 2 smaller problems. One is motion prediction, and the other is object recognition. If you know approximately where your object should be in the future, you can avoid looking everywhere for it. Once you know approximately where the object is, you can select candidates and compare how similar they look to the object you were asked to track. The candidate that looks the most like the original object is then selected by the tracking algorithm. We focus on the second problem, object recognition. Thus, a simple motion prediction algorithm based on Kalman filtering is employed. A grid of locations and rotations around the predicted future location is then used to generate a set of candidate objects at the possible locations where the model object could be found. In order to pick the right candidate, we can use a similarity metric between a low-dimensional representation of each of the candidates and that of the model object. This is known as a Siamese network. First, the same encoder is used to obtain a low-dimensional vector representation Z for both the model object and candidates. Then, each of the representation vectors are compared against the target object's representation by using a cosine similarity. The candidate with the highest cosine similarity is chosen by the tracking algorithm. The encoder is trained to minimize the mean squared distance between the cosine similarity scores and a multidimensional Gaussian function centered at the target's position. This enforces that the similarity is high for the right candidate and low for the rest, with a smoothly decaying value. When we are assigned a target, we are only given whatever view it has when we see it for the first time. This view might be composed of a very low number of points due to either occlusion or being far away from the sensor. However, as we track an object, we will view it from multiple points of view. This allows us to form a more complete model for the target as time goes by. For rigid objects in LiDAR point clouds, updating the model is achieved by aligning the new view of the object with our previous model. We show that using this updated target model is both better than using the target as seen initially and better than using the most recent view we have of the target. One byproduct of this method for tracking is that we generate a target model that is more complete than any of its partial views. This complete view can be used during training to improve the tracking. By decoding the target model's representation into a complete shape, we ensure that the representations are semantically meaningful. Since the model representation can be used to generate complete model shapes and is also learned to be similar to partial views of the same object, the encoder and decoder can be used to perform shape completion. We show that regularizing the network by performing shape completion improves tracking. This presentation was read by an AI. Thank you for your attention.